Hi everyone, and welcome to this Edumine webinar on the role of structural geology in geotechnical mining risk management. Our presenter today is Dr. Wayne Barnett, a principal geologist at SRK Consulting with over 20 years of experience. Wayne specializes in defining the structural geology of mining projects in order to inform rock mass characterization and geotechnical engineering work. Thanks for joining us, and let's get started.
Hello everyone. Welcome to my course on structural geology as applied to geotechnical mine risk management. The objective of this presentation is to really show you why structural geology is so fundamentally important in mining operations, particularly as applied to managing risk. And to also illustrate how to define the structures that you see in the mine and analyze them and present them to the geotechnical engineer who will want to use your understanding of the structures for their particular mining studies. Yes, ultimately structural geology and its related problems can commonly be managed or engineered at a cost, particularly if it is identified earlier enough. But they can cause operating costs or risk to escalate beyond the tolerance for that mining operation, and in some cases even cause premature project closure. Fundamentally though, the geology input is really what underpins every aspect of the mining process and the geotechnical design. You can talk about the input of geology into the 3D resource model. You can talk about the input into the mineral processing strategy as well as the environmental strategy. And also, very importantly, into the geotechnical design. The lithology, alteration, structures, and information about all the discontinuities in the rock mass get summarized into what we call a geotechnical domain model. That domain model then is the input into your slope or your underground design. So, getting straight to the point, faults are not straight lines. Basically, fault systems are complex with variable properties and patterns and continuity. So, that's what I want you to remember throughout this particular course, is the focus on pattern properties and continuity. How do you describe these aspects of the fault system to the engineer? All right, the pattern could have different structures and different orientations. The properties could be variable, could be weak or strong along that fault system, and the continuity can be quite substantially different depending on which structures you're talking about. Okay, and while you're doing this, you need to think about what do those patterns, properties, and continuity look like in 3 dimensions, because fundamentally your 3D interpretation does not start at the computer when you have all that information uploaded onto your computer screen. The 3-dimensional interpretation needs to start right here at the rock base, where you need to be thinking about how those structures interact and extend perhaps to the next drift or to the next part of the slope. So one of the challenges though is, how do you capture your 3D interpretation on paper or electronic tablet? So again, I want to really emphasize these first 3 components of structural geology: the pattern, the properties, and the continuity. All right, the pattern is what mapping and interpreting in 3 dimensions the orientation of the structures as it would be formed within a specific structural setting. Okay, and there may be foliations that you mine. There's whatever structural aspect is important. What is the geometry and how do they interact in some form of pattern? The properties, how do those properties vary along the structures? Okay, and there may be different sets of structures or types of structures with different properties. And then the continuity. right, can the pattern and the relative timing, those cross-cutting relationships between the structures, can they help you determine or understand the continuity of the structures? So this is what I call the PPC, and we're referring to this brief acronym throughout. The PPC, pattern, properties, and continuity, gets summarized then into a final product that needs to be provided to the engineers, which is the domains. Okay, those domains need to be practical. Okay, so which structures are relevant to the engineer? All right, there's an objective, there's a reason why you're collecting this information and trying to understand it, and that is to provide it to the engineer in some way that he can use it, or she can use it. So what are the PPC controls on the spatial domains? Right, that's what needs to be understood. Now, the biggest problem with me that I find when I go to mines all over the world, literally 9 out of 10 mines have this problem, is this is what their structural model looks like. You can see these structures with great continuity going straight across the mine, cross-cutting each other without any understanding of timing relationships, and this is simply not realistic. Realistic models have realistic patterns, geometries that we understand do form in rocks. We understand how and why they form. These are just some examples. This is an actual face. There's a very small little minor fault. You can see the extreme variability in the structure across the face and the secondary structures, all related to the same structural feature. Some more examples from the literature. So let's talk about patterns first. Structural geology is almost by definition the recognition and understanding of patterns in the rock. That's what we do. We interpolate patterns, we group them into the domains, as I said, and we use the understanding of those patterns to extrapolate domains into areas of interest where we actually don't have any data. So by identifying that there's a strong fault fracture system in this area, putting a domain boundary around that, and we can extend that zone to an area perhaps where the future pit's going to be. Right? That's why we need to understand the patterns. Now let's first go back another step and talk about patterns in 3 dimensions. Okay, faults form 3D linked arrays, and when they move or deform, they move cooperatively to accomplish what we call a balanced deformation of the rock mass. Okay. Too many published interpretations simply show cross-cutting faults and lineaments without any offset. That's not how faults operate. As you can see in these diagrams, that each of these fault segments, the 4 segments, are actually accommodating the displacement through that movement. And we know what fault networks look like. We've got linked arrays of faults from studies all over the world. Here's a linkage in the North Sea off the coast of Norway. Here's the fault system in the Pannonian Basin in Hungary. All right, and you can see these segments are interlinked, different patterns. These are forming as part of the same deformation system. Okay, sometimes there's multiple deformation systems. These fractures are interlinked and in many cases reactivated. And we know from simply looking at the global tectonics, such as the oceanic plate, how these transform faults and extensional structures work together to accommodate the displacement. Okay, so that's what we should expect when we look at the rock mass. So I'm not going to be teaching all the basic structural patterns here. We're assuming there's a certain level of structural understanding, right? And when you look at the rock, you'll be able to identify patterns as belonging to either extensional or compressional or strike-slip systems. Okay. Your objective often to understand the pattern is to see how the different structures of different orientation could be working together to explain the deformation that you're seeing. Perhaps it's the strike-slip movement or the thrusting or the displacements you're seeing on the fault systems. How do they work together to accommodate that displacement? Obviously, you could be looking on the smaller scale at patterns that can help you understand those directions of movement, whether they're conjugates, fault and fracture systems, whether they're radial shears within the fault systems. These will all guide you to understand the patterns and to understand the kinematics of how these systems are actually deforming. One thing that I would very much like to emphasize here is the actual process of fault formation, because it's very important to understand this when you're looking at it in a mining environment. Faults form through the process of propagation, then segmentation and linkage. So here you have a fault that's propagating upwards. Okay, for some reason, there's along the tip line of that fault, there is some retardation, and certain parts of the fault are propagating faster than other parts. All right. So as it continues to extend, you end up with two different fault segments. This is the process of segmentation. And here in this image here, you can see examples of different minor faults that are starting to propagate. There's small displacements there, and you can see that they're forming different segments. This one, however, is starting to overlap, and there's a linkage zone between these two segments. So as they extend and fracture, they overlap, and because of the stress concentrations between these segments, there's fracturing starts to extend and connect between the two segments, right? And eventually it breaches and you form a ramp. Okay, this is a zone of intense complexity and fracturing. Over time, as this fault continues to accommodate strain, may become a zone of thicker brecciation. All right, but that overlap and linkage is very important to explain the variation in properties across the fault system. So let's have a look at these examples of faults. Here we're going from a very immature fault system to a very mature fault system. This is an example from a paper we picked up, and you can see here that in this case, this very immature system's got a series of different fault segments that are somewhat overlapping but not connecting. As the deformation continues, the segments will overlap and form a single fault system with a variation in properties. And you see how complex these systems are. In this case here, we've got this mine drift that's come along and intersected this fault. And here you see a thick fault pressure. Right? Another mine drift comes across, and the mine geologist is walking along there, and he says, okay, there's two fault segments, slightly different orientation, not sure how to connect it. And this is very common when I go to the different mines around the world. In some cases, the geologists have literally given up because they don't understand why they don't find the fault in the adjacent drift, why the faults look so different, or have no obvious visual connection or similarity to the structures in the adjacent mine drifts. This is why, because fault systems are complex and they're not continuous. Okay? So here, this process of segmentation, growth, and then overlap and linkage really explains the variation we see. For example, when drilling, here we can see two holes drilling for the same fault. One intersects it, one does not. Here, one intersects one fault. Here, it intersects two faults. In this case, a thin fault and a much thicker fault. These can all be part of the same fault system. Okay, it explains the variations in orientation we see, continuity, single or multiple faults, fault thicknesses, hydrological conductivity along those faults. It explains different fault deformation textures, fault rock textures you see inside the fault systems, and it explains the variation in fault behavior we see in mining operations. For example, the presence of seismic gaps in areas where there's no fault, or more seismicity in areas where there is a fault. an important process these days of interpreting your patterns is through importing the data from underground and combining that with the observations of the patterns that you've seen in the mine drifts or in the open pit, and interpreting those patterns on a larger scale. This is a powerful new tool that we use in all our studies to understand the larger scale fault patterns, or fault patterns. And we can combine these days with stereo nets. Certainly Leapfrog Geo, for example, allows you to select your data and query it immediately on stereo nets to see how what sort of patterns are forming and how those different orientations of fault segments and structures can interact to form a system. Right, let's talk about fault properties. So this is one of the more significant factors of a fault that impacts the behavior of that fault in the mining. So you do need to describe those properties. Okay. For example, these are just examples here. So we have here a breccia, okay, with a cohesive pseudotachyte. That would be a very strong cohesive rock. Okay. This example here is incohesive cataclysite. This is quite commonly what we see in faults. Sort of a tiny little fault core zone here with cataclysite that is fairly weak, may have a very low cohesion. Okay. This is another common, we've got a planar fault with slickensides and steps along that fault indicating the direction of movement. Okay. This could be quite a cohesive fault, a fault vein system. So in many orogenic and even in some porphyry systems, you get faultful veins. Okay, and depending on the material infill here, it would have a different strength. Okay. Also, commonly we'll get these clay gouge cataclysite infill faults. These types of faults have a very low strength, and you need to be aware of that. Of course, if it's a ductile strain zone, then perhaps the strength is very high. We can certainly look at the spatial variation in properties around a mine. All right, in this case, this is a porphyry system with fault veins and fault veins. And what they've done is, for every structure, they've actually mapped and described the infill on those structures. And this map shows a color coding where you get fault gouge and very weak structures, with those with alteration in the red to yellow scale. And we have got structures with quartz infill in the blue. And you can see how clearly the strength of the structures actually domains the entire rock mass. Right? We can take those observations and paint them onto the structural model as well to see which faults are stronger and which are weaker. You can see how this would be such a powerful tool or piece of information for the geotechnical engineer who's trying to do a design on these different domains for that pit. It's something that we should perhaps think a bit more carefully about is how do the fault properties vary on a fault? And they can be fairly complex. This is just an example where this fault was drilled by all these holes. These are all the intersections of the drill holes on that fault plane. And I've color-coded again red because of breccia and gouge, whereas the blue, for example, is just fractured or rubble. And you can see that variation in properties is quite extreme. Okay, so that shows you, and perhaps this is actually an indication of a wider, thicker fault zone, and here's a thinner fault zone. And you get the idea. Perhaps it's also related to the geometry, the curvature of this fault system, and perhaps by understanding this more, we could actually link the properties, the brecciation on the system to the kinematics, or the way that fault has moved and sheared. To understand why this is so important, we need to just look at the basic concept of failure, or rock mass failure, or failure through an intact rock. So the concept here, this is just a simple analogy. We have a block sitting on top of an inclined slope here, all right? And the question is, how and when will this block slide? How and when will this fault surface fail? Okay, so what is the forces preventing it from failing is in fact the weight perpendicular to the face, the normal weight down onto the surface, holding it in place, the friction and the cohesive properties of the surface. What's causing or driving the failure is the weight component in the direction down the face, in parallel to this particular fault surface, okay, as well as any other disturbing force, whether that is earthquake seismicity, blasting, or perhaps even machine equipment. Okay, so we describe that through some form of failure criterion or an equation, okay, where the strength, the shear strength is related to the normal stress down onto the face, as well as the frictional properties or the coefficient of friction, plus a cohesion. So in practical sense, what does that mean? What are you looking for as a structural geologist to communicate to the engineer? All right. So you're really looking for those frictional and cohesive properties. Okay. That could be along a single fault. It could be between faults in a network of faults, and that might actually change over time. Okay. So the frictional observations could include observations of surface roughness, the infill width, the wall rock composition, the waviness of the structure on the large scale or the small scale. The cohesive strength observations could be, looking at the infill composition, or just giving an estimate. Do you think the cohesive strength is low, intermediate, or high? Okay. Well, how much gouge is in that fault system? These are basic observations that would help the engineer make decisions. There are a variety of geotechnical classification systems that can help you, for example, with defining surface roughness, okay, or waviness. These you can find from your geotechnical engineer or online, no problem. This is just an example. Often your ground problems are actually related to groundwater. Okay, and it's triggered by an increase in the pressure of groundwater. So how would water affect the strength of structures? Really what it comes down to is that when you've got water pressure inside that structure, you're actually reducing that confining normal stress. So you're moving, if this is a more Coulomb diagram, that's your sigma 1 and that's your sigma 3, your maximum minimum stress. All right, you actually end up reducing the normal stress and moving this whole more Coulomb diagram across towards the failure envelope. Okay, so that's why in the end you actually get failure along that fault. You can try to present these properties to the engineers in different ways. So here is a completed three-dimensional model of the structures at Snap Lake Mine. Okay, each one of these structures has been mapped and then modeled in 3D, and the properties were recorded either from the mapping or from the drill holes. And then what we've tried to do is to paint those properties onto the surface. So here, this is the infill code. Again, red is a weaker, blue is stronger. Okay, you could paint other properties too. For example, you could paint the width of the fault zones, okay, from thicker to thinner types of faults. You could paint the water presence, any observations about the water flow, or whatever else is relevant for the geotechnical engineer. One thing though we typically find is that the variability in these faults is pretty extreme. So really, do you have enough data, enough intersections to represent this in a way that is meaningful? That is probably one of the bigger challenges with this process. So think about it, and if not, you need to communicate that uncertainty to the engineer. So the third aspect of PPC is the continuity, and here there is a real challenge. Okay, so for example, let's just be reminded of all these mines we go to, and we see that in many cases the continuity in the pattern hasn't been thought about, and we've got structures going all the way through the rock mass. Or perhaps I've been asked to take some information and model a fault structure, and I thought, great, yes, I've got good constraints here, I was able to model it, but you know what, this fault could continue on, right? So interpreting this great continuity of this fault often makes the resource guy quite happy, because in the cases where these faults are controlling your mineralization, that's great news. But that could really upset the geotechnical engineer. Right? There's a significant impact to engineering design when you make decisions about continuity. Because in this case, this would impact the entire slope of your pit. So we need to think about how to constrain continuity. How do we define it so that we can build adequate models that represent the continuity of fault systems in an appropriate way? Clearly, if you do have good exposure in your pit mapping is a great way to actually define that continuity. You need to make sure, however, that when you're mapping that you are capturing that appropriately. All right. So here the map shows structures with continuity versus structures without continuity. Shows cross-cutting relationships and shows how overall the pattern and the continuity work together. Okay. So you need to focus on that when you're mapping. Of course, in many cases, you can only just access the nearest bench in the pit and map what you can see. But modern technology is introducing a whole new dimension to our data capture. And we can use LiDAR and photogrammetry data sets, sometimes from unmanned airborne vehicles, UAVs, to scan and produce three-dimensional images of our pits. And you can import these into certain software and actually digitize and measure the orientation of structures and define the patterns and the continuities. Right. Also, simply by understanding the patterns and noting the relative timing and cross-cutting relationships, we end up creating a model that is more representative of reality. Where we have structures we know cross-cut the other and offset other structures, structures of different age. This is what the structural geologist needs to do to understand how to think about the continuity when modeling this in 3 dimensions. Right? Understand that there's an older fault system here, for example, that is being cut by the younger fault. Other evidence can come from the large-scale patterns, for example, aerial photography, from aeromagnetics. Perhaps you can take your satellite images or your orthophotos, you can actually drape them onto LiDAR topographic surfaces these days, and you can map out these structures, you can map the continuity. In this case, at this mine, the belief was that these structures actually extended down and through the pit and would have a huge impact on the pit stability. But by simply mapping and looking at these segments, we see the lack of continuity. We see that they often stop and sidestep into a new structure and therefore have higher rock mass strength than what was believed. Very important to understand that continuity. There are other techniques. This is a very old school technique of drawing form lines. Form lines help you in areas where the contrast in the rock are not that obvious and you can't exactly place where the faults are. Try this out. This really works well in photographs of areas that you can't quite work out what is going on. You just need time to sit down and trace out the different form lines and work out what is going on. It's an underutilized tool these days. Right, obviously the drill hole information is the drill holes are there to help establish continuity at depth where you don't have exposures. So make sure you got the right data, right? Very importantly is to make sure the structural logging is done appropriately so that you can identify those fault intersections, bring them up in 3 dimensions and use them to work out the continuity of the structures. You may also use other aspects of the logging such as clay alteration. Here we've got a clear definition of a fault system through the alteration in the clay. Or fracture frequency, two beautifully defined faults are defined here with a little bit of an offset of this fault against this fault. All right, drill hole or borehole assays commonly can be used to, if insufficient density, can be used to define fault systems, or simply using RQD to define zones of faults. The best way to fully understand a fault system is to have a fully integrated lithostructural model. In some cases, however, you may not have the logging that actually have picked up the structures. We go to many projects where the structures have not been adequately logged. So we've got to find other ways of predicting where those structures are. And certainly by understanding for example, a volcanological, sedimentological system and how it formed, and looking at variations in thickness of different volcano-sedimentary packages, we can infer the presence of certain faults. Of course, you need to communicate your interpretation with a level of confidence as well. Ultimately, though, it often comes down to how well do those intersections line up in 3D to define that fault, right? Because you're really trying to choose between the situation where you've got a long continuous fault or different segments. And if you don't have the mapping information, then you're going to be guessing. And remember that just because it lines up very nicely does not mean that your interpretation is correct. This is a great example from an open pit. You see different fault segments, and if I had one single drill hole through there, you would see the 3 intersections lining up. That does not mean that it is one continuous fault that could impact the entire slope, as opposed to these separate segments that won't impact the entire slope. So think about what is the confidence of your interpretation, and how do you interpret that to the engineer? Because communicating to the engineers can be one of the most significant challenges in this job. Typically, the geologist is very passionate, excited about his interpretation. Fantastic 5 phases of deformation and tied back into 1 billion years of Earth's history, and he's very excited about his overall understanding of that system. Whereas the engineer is only really interested in what is relevant, what is important for the design of that pit, and what is your confidence in what you've interpreted. What can he rely on for the design? So the final product that you hand over is almost always a domain model of some sort. A domain model is a simplification of reality, maybe different domains or segments for a pit or an underground mine where the properties of those domains can be grouped, classified, or presented statistically. Okay, in this example here, we tried to produce an understanding of the variation in joint patterns. These are the hatching between these different fault systems. Okay, and perhaps what you do is present these different joint patterns as sterionets and sort of summarized for different domains around that particular mine. Okay, and those domains would be defined based on your 3D structural pattern, the properties of those structures, and the continuity. Okay, they may be related to the structures, or or perhaps those structures are the domain boundaries. It's important to try and understand that. So once you've got your domain, what you may have to do is to actually summarize those properties for each of the domains. And if you're talking about the orientation of the structures in those domains, the pattern, then you can represent the pattern on the sterionet. you're talking about the properties of the structures, perhaps you want to represent that on some sort of diagram that shows the relative percentage of different types of properties and the importance. Okay, in many cases the engineer needs to know the frequency of faults or fractures, and perhaps you'd want to represent that in some sort of histogram. The other important aspect here that we must not forget is that we use domains to extrapolate patterns into areas that we do not have information. The problem is I'm often asked by clients to interpret these structures and go map these structures in, let's say, the current pit. And then they want to know what are those structures in the final future pit. Let's say here, down here, 200 meters below the original pit. And yes, you can take your big major structures, the ones you know of high continuity, and you can probably extrapolate those down to the future pit. But they also want to know about the smaller second order structures. And the problem is you should not and cannot interpolate those structures down to those depths because they don't go down there. But you may know that the pattern of structures does go down there. So what we do is define a domain. We describe the domain and we then explain to the engineer what that domain will look like at depth. Okay. Another important aspect of geotechnical design is understanding the rock mass rating, right? For those who've undertaken or heard of rock mass classification systems, structure is an important part or an important input into those classification systems. Sometimes its focus is more on joint systems and fracture systems, but joints and fractures are part of your structural system. And you understand the joints and fractures by understanding your fault structural system. You may need to understand the spacing, the infill properties of your joints and faults, as well as those conditions, in other words, the roughness and infill properties and the overall large-scale waviness of those faults. Okay? And help the engineer define the rock mass rating. This would be used ultimately in, for example, in some sort of block models or just design sections off the pit or the underground mine to represent the strength of the entire rock mass in different areas and base your design on that. In many cases, the information about fracture frequency and orientation also get used in discrete fracture networks where the engineer tries to simulate the discontinuities in the rock mass using the information that's been provided. So you need to find out if that is the objective and make sure that the data you collect is adequate for that particular purpose. And don't forget to map domains. While you're mapping, look at the changes in properties, changes in structures and orientations. See why is that happening. In this particular case, we have a sequence of structures with greater continuity running in that direction, and then in this domain we got a change in the orientation of structures. There must be a reason for that, and you should map that. So think about how do you map patterns. Most mines I go to, people don't map patterns. All right, it was usually best practice decades ago to show all the changes in patterns or the changes in orientations of your structures and the continuities in a nice detailed map. Nowadays you can still use paper. There's nothing wrong with that. There's also electronic tablets that we can use to map onto, all right, and to draw in the same way, and then more easily get into a three-dimensional environment or into a two-dimensional ArcGIS environment, somewhere where you can interpret, you can bring your interpretation in and then bring that into a three-dimensional environment and complete your overall interpretation. At the same time, you can map and bring in the properties of the structures, perhaps dropped into some sort of database system, or in this case this is an ArcGIS table. All right, and that information is then available in 3 dimensions to make your final interpretive decisions. Fault zone domains. Okay, this is a fault zone. Here's a fault core, and that's the damage zone. Okay. Don't forget about these damage zones around the faults. The fault is not a single point. There's a core with a certain width, okay, that may be close to 0 width, or it may be many meters wide. It also has a damage zone around it, an influence zone, a zone where the rock mass has been impacted by additional fracturing and probably minor faulting, and that needs to be described. The engineer needs to know about that. Here's a great example in drill core. You've got the fault zone in the middle here, and you've got a damage zone that gets progressively weaker in effect away from the core zone. As the engineer approaches this, they would think about this as being the weakest rock mass, okay, classified as the weakest rock mass, perhaps in red here, and as you get away, the rock mass improves. Okay, as the structural geologist, you understand this much better than the engineer. You understand why it's there. You can define these domains, whether that's underground or in core. You need to be thinking about that and how you map it or log it and present that to the engineer. Here we have another example in the pit. At this particular mine, they had in fact mapped a fault there and a fault there. That was the only information available for the engineer to use in their design, and it's completely wrong, right? You have a fault zone, fault core, probably over 10 meters wide in this area, full of clay and gouge and breccia. Okay, you've got an intense damage zone on either side, and in fact there's even a wider damage zone beyond that. That's what needs to be described and understood. Map the domains, map the zones, the fault zones, and the damage zones. Fault damage zones form in a variety of processes. Okay, in brittle faults, brittle fracturing occurs in those areas wherever there's strain concentration, right? So we already spoke about those linkage zones between different segments, right? Such as here, this is a linkage zone, stress concentrates in there and you get damage, all right? With extensional fractures connecting the two segments. You may get irregularities and roughness along the main fault system with the formation of faults and at those stress concentrations. Even at the tip, where the fault is propagating, right at the tip zone, you get damage. Okay, where multiple faults intersect and overlap, you'll start to get damage. This is a nice example from Peacock et al., which shows how they've mapped the frequency of fractures along the fault system, and you can certainly see where the high damage zones are, and it really illustrates the variability in the properties along a fault system. Okay, here up close you can see two faults approaching and the stress-induced fracturing that causes that complexity. Again, these are the areas of greatest fluid permeability. If you're looking for mineralization, that's where you go look for mineralization. If you're looking for groundwater, because you want to depressurize the slopes and you want to put a drill hole in there, that's where you go looking for the groundwater. So, nice simple illustration of permeability of groundwater along faults, and here's the fault core and there's a damage zone. Here you got many fault cores with an extended damage zone around or influence area around those faults, and as the fracture density increases, so does the permeability. Often right on the fault core itself is a lot of clay and the permeability drops to something negligible. All right, but those damage zones are actually fundamentally important in terms of understanding groundwater flow and even in terms of rock mass strength. You don't want to forget about rock mass strength anisotropy. Certainly the development of the foliation in the rock is a fundamental part of structural geology understanding. That foliation is actually a direction of weakness. Now, whether it's simply bedding like this here, where you can see how it's influenced the slope, or another anisotropy like foliation, it's important to understand its orientation. Okay, because that's the strength of the rock mass is different in different orientations. For example, this is from Yarrick in the SRK office of Vancouver, who was illustrating here that the weakest direction is probably pulling it apart in that direction. Okay, there's a low strength in trying to shear this rock along this foliation in this direction with this fold undulations, and the highest strength would be across those undulations. Right. Nowadays, what we can do is we can take our measurements, whether that's bedding or foliation, and we can produce formed surfaces, three-dimensional representations of that. You can take the orientations of each of the triangles, each little piece of these surfaces, and create a block model and paint those onto your pit. In this case, you can see areas of higher angle, or the redder color representing steeper areas that may have been higher risk to your pit, and the blue areas being lower risk with lower, shallower dipping structures. Okay, can be really useful for defining domains and for educating your engineers to the properties of the rock mass. Ultimately, you've got to think about communication. There's probably a number of ways to do it. This is an example from Campbell et al. In 2015, where the idea is to define a structural matrix where each of your identified faults or fault sets is described, okay, in terms of the orientation, the thickness, persistence, the continuity, the infill properties, whatever is important to engineer can be put in here. You can talk about the patterns and the timing relationships and the domains, and you can talk about the confidence. So what data was informing your interpretation? How many drill hole intersections? What mapping? Was there LiDAR information? Was there satellite images? What was it that helps you define the continuity of your major structures? You can do the same with your minor structures, right? So we're talking about the physical characters, the spatial arrangement, the confidence, right? And then the last step is you have to make sure you don't simply throw this at the engineer and run away, but you talk to them and you explain to them what it means, and you talk about the risk. So you close that loop, right? You make sure that the potential impact to the mine or the mine design is understood by the engineers, that the geologist understands that and can, if necessary, go back and get more information, right? Or improve the model through iterative phases to get to a point where it's adequate for the design. Okay, so as we move towards some more practical examples of how structures impact different types of mining environments, let's just talk about the basis for how structures impact rock mass behavior. It's because mining causes a redistribution of stress in the rock mass. You create a big hole in the rock, and then it's got to respond to that, because the stresses need to stay balanced, and you've basically put the stress out of equilibrium. Okay, it needs to re-establish some form of stress equilibrium. So if there's structures in that rock mass while it's trying to establish a new equilibrium, those structures may accommodate some strain. Okay, so this creates really a dynamic four-dimensional situation where structures that were not relevant before now become relevant and start to interact with each other, interact with the mining excavation, or become a factor that needs to be dealt with by the engineers. Here we've got an example with the mine excavation and a tunnel intersecting, and you can see how the stress has accumulated a lot, or strain, sorry, this is a model of strain, how strain has actually manifested along the fault surface. Okay, it's also important to keep in mind that that deformation, as it's trying to re-establish its equilibrium, the rock mass is deforming progressively. Okay, so for example, if you simply cut a tunnel into the rock like this, perfectly circular tunnel, you'll start to get stress concentrations along the side, and slowly the rock would begin to fracture, right? Those fractures would propagate further and more further away from the edges, and perhaps there's a fault there, and the stress moves ahead, because as the rock fractures, you actually reduce the stress and move the stress to an area where there's no fractures, right? And perhaps that would cause strain on a fault system. So that fault may not react immediately as the tunnel is developed, but may react at some point in time. Here we've got an example of fault system running through several, at least two stopes here, and you can see how in this area the fault hasn't yet reacted, but in the areas where the stope is, it is reacting. Okay, there are examples, for example, in the deep level mines in South Africa, such as Durban-Roodepoort mine. Here we have, as the tunnel developed towards this fault dike system, the seismicity increased, and once it got through the dike system, the seismicity dropped, right? So that fault is allowing energy to be released as you interact with it and create strain across it. Here's an example from Palabor mine. Their initial pit, there was no problems in that pit. They mapped features, structures, but there was never any issue. But when they started to develop the underground block cave, they changed the situation. They changed the stress-strain regime, and suddenly this fault appeared in the pit that had never been worried, it never moved before, it never impacted anything, and it caused a major slope failure. So over time, you change the mining environment, you can then create a situation that you may not expect, where structures are influencing the rock mass behavior. So let's talk about structural risks in surface mining. Okay, the types of risks are usually slope failure, all right, with a variety of different geometries we'll talk about, and also water inflow is important. Okay, typical failure scenarios we often talk about is the planar, wedge, and toppling failure. All right, and these really are governed by structural pattern. All right, obviously the properties of those structures are also important. If they're strongly solidified or well sealed, then the structures probably wouldn't fail. But if they're weak with gouge, then they're more likely to fail. The other important aspect here is the continuity. This is a great diagram from Sullivan 2013, just showing how different structures of different continuity impact your slope and your slope design at different scales. So small structures, third order structures, joint systems, for example, will impact your bench design. Larger structures, say second order fault systems, could impact your inter-ramp design and the stability of your inter-ramp stack. And the larger structures can impact your overall pit stability. This is an example here where this pit could not get down through this fault system over here. And eventually, once they broke through, they were able to cut down at a higher, steeper angle. But the properties and the orientation of that fault system prevented the slope from achieving its original design angle. There's more examples. I recommend further reading by this great paper by Doug Stead and Volter, 2015, showing different types of geometries and scenarios with different forms of failure within pits and in unstable terrains. They also talk about how faults can impact the stability of the rock mass, okay, depending on the orientation, the inclination of the fold axial plane, or the plunge of the hinge line. Okay, these geometries that can impact how rock mass can behave. This is a common scenario. Here's an example in an open pit where this is actually foliation is intersecting a fault plane, and the two form a wedge, and this entire edge of the slope just fell out. So when involved in designing pits, you need to think about these. Where is the position of the fault? What is the geometry of the slope? Clearly, in this case, this would not be good. Here you've got an confined bulge in the slope, and you've got a fault behind it. This is a very likely scenario where you'd get a failure. Right, so here's some more examples. You've seen this where the fault zone's controlling the slope. Here we've got, you can see different domains. Here you've got a massive fault shear zone, ductile system, reactivated a brittle fault system. And you can see how the rock is behaving differently. Here you've got a dolerite sill that's stabilizing the slope. Okay. All right, if you're talking about folds, clearly the geometry can impact the stability of the slope, not just its orientation, but also its amplitude and wavelength. In this case, this waviness, let's say this is bedding, and this is the gentle folding in the bedding system. You can see that it's perfectly angled to create a instability in that stack. Right? Low, or let's say low wavelength, high amplitude structures could help create roughness, but depending on the orientation, in this case it probably would not help stabilize the slope. In this case it might actually in fact create the right conditions to prevent slip on this bedding surface, for example. It's quite common to have situations where you've got structures or features, let's say that's bedding or foliation, that is creating problems in one sector of the pit and is helping stabilize the pit in the other sectors. You need to think about the orientation of the plunge of the folds. Right? In this case, this would be not favorable for the stability of that slope. Here's a good case study from the Highland Valley Copper Mine, and this is the Lornex pit, and what you can see here is the deep-seated failure within the slope. You can see how parts of the slope are rising up and parts are sinking down, creating these obsequent scarps. There's quite a complex fault system here with a Lornex fault system at depth, and when they modeled this, they were able to show that there's a large number of secondary fault structures feeding into basal fault system, and what we're getting here is known as toppling failure. So as you can see, the segments blocks to the high wall side are rising up compared to the parts lower down, and you're getting basically a circular rotation process which is known as toppling failure. Okay, this is quite common in large, complex faulted slopes. Right, so talking quickly about groundwater. Groundwater can be very important in slope stability. Certainly in areas where you've got rock types with low permeability, you can't drain those slopes easily. Right? Areas where you can drain the slopes, you can reduce the water pressure and you can reduce the risk. In areas where you can't reduce the water pore pressure, you retain pressures in that slope and that can cause problems. Structures can also compartmentalize your water flow. In cases here, we've got no compartmentalization. You drop the water pressure down and you reduce risk in that slope. In these areas here, perhaps you've got clay gouge on those fault systems, which is preventing water flowing across those fault systems and allowing the rock to retain poor water pressures in those slopes, which can increase risk. So here's just a summary diagram of the problems, the risks in open pits. We got situations perhaps where bedding is helping to control failure. Perhaps these bedding parallel faulting can help control failure. We've got situations where you've got foliation. Here we've got a strong foliation developed in the rock mass. In certain parts of the pit, it will prevent stability, and particularly the benches after blasting. blasting can have a great trouble actually preserving the crest of these benches when you've got such a strong anisotropy in the rock mass. Perhaps you've got zones of, or domains of increased intensity of faulting and fracturing, and you've got situations where you could get toppling failure. Here you've got a plane of failure situation with a releasing fault in the back, all right, forming a tensile feature. So look at the combinations of structures and the orientations and how they could create risk in your open pit. Right, let's talk about massive mining. Particularly we're talking about block caving or sub-level caving type mining risks. The aspects we look at is cavability, angle of substance, large-scale wedge loading, caving direction, and mud rushes. Right, so the idea behind block caving is that you create a undercut level where you simply undercut the rock mass as wide as possible to allow it to start to fall down on its own. Right, when it falls down, it breaks and fragments the rock. So the objective behind block caving is to save on costs from blasting the rock to fragment it, to let gravity and stresses and point load stresses that build up on the broken fragments to further fragment and reduce the size of the rocks to a point where it can come through these draw points underneath. So we've come underneath with a production level and created draw points, and we're allowing the rock to flow through those draw points underneath to be loaded and removed from the mine. Okay. So one of the key questions when the design starts is how will this rock mass fragment? Okay. Will it fragment? What sort of size of excavation do you need to create a situation where the rock will collapse and fragment? Okay. And what is going to be the size distribution of these big particles as they come down through the draw points? To understand that, you need to understand the structures in the rock mass, not only the fault systems, but quite commonly the joints and the vein systems. Okay, and you need to understand the orientation, the spacing, the persistence of these structures, how they terminate against each other, and how many different types of sets there are. Really what you're trying to do is define the shape of the block, these joint fault-bounded blocks that are going to be forming in your cave. On top of that, what helps understand whether the fracture or not is information on the shape, filling, aperture, the strength, and the amount of water in the system. Ultimately, you're trying to predict what is the block size distribution going to look like. Okay. As the cave starts to propagate and grow, all right, the angle of that cave and the shape of the cave is also dependent on the natural weaknesses in the rock mass, your structures. Okay. In situations where the rock is poorly fragmented, you could have formed gap. You could actually stop the fragmentation and stop the collapse process, and it causes large gaps. This is a high risk to a mining situation because at some point a big block could simply fall out, pushing the air through your tunnel system. And in the case of, for example, North Parks, there was severe damage and loss of life. So this is one of these high risk scenarios that block caves tend to want to avoid. Right, this is the Cassia mine in the Yukon. This case study again from Jarek Jakubek in SRK, and in this example, it's a serpentinite mine, and what we're trying to do is understand the orientation of the shear zones, but the serpentinite is very weak and highly altered. So our weakest rock here, this class 5 rock mass rating rock here in orange, is in fact their shear zone through the serpentinite. Okay, and that's what it looks like. Right, so imagine now we're undercutting this rock mass, and in this scenario we're starting this side and moving this way. And these are the large shear zones coming through here. We undercut it, and what we create is a big wedge that can simply sit down and squash your tunnel infrastructure there on your undercut and development levels. This is not the ideal situation. This happens in mines, and It's due to not basing your cave propagation direction. So this is the direction in which you do the undercuts and move the undercut. All right. If you don't understand the orientation of the structures, this is the type of risk that you could face when developing the mine. So, just to make the point further, if we had in fact started the undercut on this side, we would have caused this part to fragment, and you would never have formed that wedge in the first place. So that is why the direction of undercutting is important if you've got structures in your cave. That's what it can look like from cave wedge loading. This is a situation where this tunnel has just been squashed. All right, it's a huge amount of cost to redevelop these tunnels, and in many cases it's extremely difficult, if not impossible, to recover your caves. Structures also feed water into a block cave, and if not drained properly, or if you don't do proper draw control to keep the water flowing, the mud can build up and then eventually release as a mud rush, which again is a very bad, dangerous situation, and many people's lives have been lost due to mud rushes. Okay, let's talk about shallow mining and the risks involved there. So there are many methods of partial and full extraction, and the type of risk we really talk about is key block failure, unraveling, backbreak on fault systems, surface subsidence, and water flow. Right, so here we've got an example 3D structural pattern that is controlling wall failure. Right, these are typical key block analyses that the geotechnical engineers will do to define what sort of rock reinforcement or support they need to put into these tunnels to prevent these blocks from falling out. So understanding these structural patterns will help them with the design and the reduction of risk in these particular tunnels, or within shafts or ore passes. This is a good summary paper from Schober et al. 2012, which lists all the different types of stope roof failure. Right, there's quite a variety of examples there. Typically, they're structurally controlled, or zones of weakness, or domains or small domains of low rock mass strength. Okay. Here's an example of backbreak in a stope. And these structures here have cut the hanging wall and caused blocks to fall out. Okay, that's why these structural zones need to be adequately identified, the orientations identified, so that you can put in the appropriate anchors to prevent the failure. Sublevel open stoping, however, you tend to create big open excavations, difficult to rely on reinforce this rock, right? So understanding the density or the continuity of these structures before you design this is very important, because it will have an impact on the safety in those stopes, as well as potential dilution of your ore as you're trying to mine it. Okay, you can, being quite shallow and near surface, it's quite easy for you to tap into groundwater near surface. You simply hit the wrong structure that is linked to the groundwater table, and you can get water and even mud rushes from fault zones. Here's an example case study from the Holder Potash mine in the DRC. Okay, and here what we see is that there was a small water flow appeared on a very small fault, the development end, on June the 18th, 1977. Okay, it started to rapidly increase in water flow, and the mine was evacuated on June 22nd. Right, this is what it looked like when the water started to flow through. Okay, here's the mud rush, and by June 27th, these sinkholes had appeared at surface. Why did this happen? Well, here's a tiny little fault that intersected in the development end, but unfortunately that fault was linked to a overlying dolomitic series with a lot of water within that system. All right, this rock below there was evaporitic, and as soon as the water started to flow through that fault, and that fault was connected up to the overlying water in the dolomites, that water eroded and created a wider and wider channel, allowing the water to flow through into the mining operation, and created that scenario. So unfortunately, even the smallest little faults could be problematic. We need to understand the patterns and those risks and identify those risks beforehand to put in the right risk management processes. So here is a quick summary of, in shallow level mining, how does the structural patterns and properties really help us with the mine design? Well, one of the key things here is to make sure that you plan the mining layout to account for the orientation of the structures. Normally it's best not to orientate the structures, orientate the tunnels parallel to your structures, but to try get as perpendicular to your structures as possible. This reduces the need for support and creates greater stability. If you've got a major fault zone or shear zone, normally what they would do in shallow level mining is use that as your pillar. So you not try and mine underneath that because of the poor ground conditions, but create a pillar and mine everything out. You need those pillars in order to create stability in your mining environment, and sometimes those shear zones in fact contain groundwater, so rather not mine out those areas, that just increase the risk. Right, in the final example is in deep level mining. Right, and here we've got a situation where you face risk from rock bursts, mining-induced faults, and an overall mine-scale seismicity that needs to be understood. Okay, so one of the interesting things here that's different between shallow and deep-level mining is that although the stress magnitude increases with depth, the stress ratio tends to decrease. That means that the difference between your vertical and your horizontal stress actually decreases. So why is that important? Well, because for fractures or faults to propagate, you actually need high deviatory stresses. You need differences in stress in different directions. That's what helps drive crack propagation. If the stresses are similar, then you tend not to open joints, you tend not to create more fractures. Okay, so the natural state of the rock at these depths is different. But when you create a mine, you create a big hole in the rock at depth, you obviously do create a situation where you create differences in stress in different directions, right? Which induces more volatile situation where structures can react violently and create seismicity. So, it's been stated that in scattered mining in structurally complex areas, virtually all seismicity takes place on structures. That's the natural place for the deformation to occur along pre-existing weaknesses, so they tend to be one of the dominant controls on seismicity. Okay, we talk about it, excess shear stress, and it's the old-fashioned concept, not so commonly used these days, but it is really an estimate, a measure of the amount of stress that can be released as strain energy when you're mining along a certain fault system. Okay. What we find if you look at your mine sequencing and how we're mining in different areas, you see that here, for example, this is a map of microseismicity. You see that it's actually changing from area or zone A to zone B to zone C as you mine in different parts and mine at different times. So there's a close interaction between where is the risk, where is the seismicity, and where are you mining. So knowledge of the mine sequencing and what sort of stresses, changes will happen in your mine is very important. If there's a structure, this is what can happen. You can get a rock burst. Okay? Extensive damage. Even small faults can cause a kilometer of damaged infrastructure. This is a very costly thing. So it's something that you need to understand and to model. And you need to understand where the structures are, what are their orientations, and what are their properties. Okay? This is not a real fault, a natural fault anyway. It is a man-induced fault in a pillar in a deep-level mine, also known as Ortlip shear, after Ortlip, Dave Ortlip, who actually photographed this and categorized this fault system. So here the stresses are high within that pillar, and it's caused this shearing to happen. Okay. So when you talk about seismicity in a mine system, you're really talking about the entire system and the stiffness of the entire system. And because of the complex geometries, that is a very complex discussion and a very complex thing to model. But often those patterns are related to the structure, seismic patterns are related to the structures in combination with the mine geometry and the mine sequencing. And here you can see an example of concentration of fault seismicity along a fault zone, for example. Okay, so the rock behavior here is a full 3D mining problem requiring a full 3D understanding of your structures and your lithology. There's an example, such a study in Buick et al. 2009 that you can look at. Ultimately, unlike shallow level mining, what you generally want to do is mine the fault zone. It's generally considered best practice to mine the fault zone first and then get away from it before the stresses concentrate too much and cause problems, and never go back there. If you have to mine towards a fault zone, then generally you'd mine it obliquely or at an angle. Do not come at it in a straight perpendicular direction. Okay, it's good to develop hazard maps based on the modeling to show where those areas of greater risk are, and these maps are usually produced by a proper understanding of the fault structures and an understanding of the mine sequencing again, and how the stresses, and modeling how the stresses will behave. Right, so that concludes this introduction into how structural geology impacts risks in mining. It's obvious that structural geology is a critical input into understanding how the rock mass behaves in mining. Right, there are some fundamental observations that we've talked about, the pattern properties and continuity that need to be defined, right, and then to build that into full 3D models that can be visualized and be given to the engineers for their designs. It's really only then through the integration of the structural geology with those geomechanical models that we can design the mine to reduce risk. Thank you.